Hello everyone. Thank you all for being here. My name is Ye Xianfeng from the National Taiwan University. And the topic to be introduced today is code verification of strong colon and weak bean. This is online. First of all, we will explain the concept of strong colons and weak beans. Here, there are two patterns of failure mechanism below. The first one is story mechanism, and the second one is beam mechanism. In seismic design, we hope that the structure can have large deformation to dissipate energy, but not lead to collapse when the earthquake comes. So, the best failure mode of a structure is beam mechanism. Its behavior will satisfy the concept of strong colons and weak beams. Therefore, we assemble some characteristics of this concept. The first one, reduce the likelihood of yielding in columns. Second one, minimum flexural strength of columns. Third one, avoid the structure to collapse. Secondly, we will review this code. ACI 318-14 minimum flexural strength of columns. The flexural strength of columns shall satisfy this inequality. That is, the sum of the nominal strength of columns should be larger than or be equal to 6/5 times the sum of the nominal flexural strength of beams. And we illustrate this equation as figured below. The first one is the friends west to the right, and the second one is the friends west to the left. And due to the positive and the negative LNB are usually not the same, so we need to consider both of it. Follow the ACI code. If we follow the ACI code to establish the ETABS model, we found that the results are all beam mechanism. One flow structure or two flow structure. Thirdly, check moment capacity. We will verify whether the specification is conservative. So we ask this question, whether the code referred to 1.2 times is enough. In previous ETABS example, we know that the 1.2 times is not enough. So here is an example, and there are some structural descriptions. And among them, the most important thing is that we assume V shear larger than V flexure. That is no shear failure. And there are also some dimensional descriptions. In order to satisfy the code, we design flexural strengths of beam and columns. Check mechanism. Based on the previous assumption, we want to know which failure mode will happen. So the ideal situation is no story mechanism. In here, we take out one of the frame columns as free body, and we use the direct moment equilibrium to get the best shear V by take moment equilibrium about point D. Check moment capacity. We found that the MC first forward at the top larger than MNC, so it occurs flexural failure at top of column. So the failure mode is a story mechanism, not good. Therefore, we verify that the column of first floor occurred story mechanism before the bin mechanism took place. Fourthly, we will derive factual stress ratio of columns to bins. Modify the factor, and here we carry out the same analysis, and we assume this equation to satisfy the code. And similarly, we also use the direct moment equilibrium to get the batch shear V. And we require that the MC first floor at top smaller than MNC. In this way, the failure mode of the structure will become bin mechanism. And from this inequality, we get the amplification alpha larger than 1.5 to satisfy this code. Verify the result. If we take alpha equal to 1.6 larger than 1.5, which we derive, we found that the MC first floor at the top and the MC2F at the bottom smaller than MNC. So the results are all bin mechanism. Extend the case to nth floor. We sum up the steps to find the amplification alpha in different floors. So here are some steps. The step 1 is choose the controlled mechanism. We use the direct moment equilibrium to get the batch shear V. And step 2, we set the inequality to ensure no story mechanism. We hope that no plastic hinge occurs at both ends of columns. And step 3. Finally, we will get the amplification factor alpha. Ratio of MNC to MNB for 1 to 5 floors. We induce the results into this table. From this table, we found that if alpha smaller than alpha 1, the red circle, it shows that the first floor is story mechanism. And another case, if alpha larger than alpha I, this is the green circle, it shows that the ith floor and its lower floor are all bin mechanism. And among them, the alpha sub I is no fractal hinge occurs at the top of column of ith floor. Verification. Furthermore, we will use the software called ETABS to verify our derivation. Pushover analysis by ETABS. We perform a linear pushover analysis. And here is an example of story mechanism showed in ETABS. So we verify the result. The figure is the one floor structure with alpha equal to 1.2, and this is the value of ACI code. And in ETABS, we found that the result is story mechanism at the first floor. And from the table, we also get the same result because alpha smaller than alpha 1, that is the one floor structure. So the result is story mechanism. It's consistent with the ETABS. And similarly, if we take alpha equal to 2.2 from this table, alpha larger than alpha 1, so the result is bin mechanism. And if the structure is 2 floor, and we take alpha equal to 1.2. That is the ACI code. And from the table, alpha smaller than alpha 1. So it shows that the structure is story mechanism at first floor. If we take alpha equal to 2.2 and larger than alpha 2, so the second floor and the first floor are all beam mechanism. If we take 1 alpha equal to 1.65, that is between alpha 1 and alpha 2. So if alpha larger than alpha 1, the first floor is beam mechanism, and also the alpha smaller than alpha 2. So the alpha 2 is the story mechanism here. The exact result is consistent with this table. Finally, we will give some recommendation and conclusion. First one, from the previous example, we know that follow the ACI code is insufficient. So in this paper, we recommend larger alpha I to make sure hinge occurs at beam ends firstly. And finally, the similar concept, that is the direct moment equilibrium, is able to extend the case to higher floor. This is our reference. This is all my presentation. Thanks for your listening.